for energy density fluctuations. Okay? Then we saw that there were two scales, the gene scale and the horizon size. Then we can talk about radiation and matter separately. If we look at matter, because the speed of sound is similar to the speed of light, the gene scale is of the order of the horizon always. So the question is only if perturbations are larger than the gene scale, modes are larger than the gene scale, or smaller than the gene scale. If they are smaller than the gene scale, then we saw that we get oscillations. Okay, pressure wins. Remember that. If they are larger, then we get growth like a squared. In radiation domination, if you plug the dependence of a, so the scale factor on time, and you solve the equations, that's what you get. If you look at matter, because the speed of sound is very small, the gene scale is always smaller than the horizon. So all relevant scales are larger than the gene scale, and so they all grow. Okay? The question is how much. So if we look just on the matter perturbations, in matter domination, radiation domination, and whether they're outside or inside the horizon, in matter domination, matter dominates the potential. And since there's nothing about the horizon that matters here, the growth is always as a factor of a. Okay, this again you can solve. The difference between a squared and a here is because the expansion is faster during radiation domination than in matter domination. And then in radiation domination, what matters about the outside or inside the horizon is what happens to the radiation. Because what dominates the potential, in this case, is the radiation. Okay? And then there are two options. Either we are inside the horizon, where in the radiation, the pressure wins, and delta R did not grow, and so the term with the potential doesn't matter at all, and then we only get the friction term and this term, and so we get only a logarithmic growth, or no growth at all, effectively. Or, in the other case, again, radiation-dominated potential, delta M grows just like delta R, okay? So it grows like a squared. All right. So this is a summary of the first part of the last talk. And then we deduced this from the last two talks. So this is the angular power spectrum of the temperature fluctuations in the CMB. This is what we actually see. But if we take away the damping, ignore the damping for a second, which is a result of adding the baryons, okay? If we ignore the damping, this is the potential envelope that we saw as an effect of exactly this behavior here. Then we saw that in the matter power spectrum, there's this rise and fall depending on whether scales are entering in matter domination or in radiation domination. And when you add the baryons in, you get damping. Okay, so this is the damping. And you also change the peak ratios because of the inertia that the baryons inflict onto the photons. Okay, for example, if you compress and decompress, as you decompress and you want to compress again, the baryon inertia prevents the photons from compressing as easily as they would if they were not tightly coupled with baryons. So from the damping or from the peak ratios, we can get rho B. From this, we can get rho M. And we also saw that we can get from the total matter power spectrum, we can see the wiggles showing up here. Because if you think about things in real space, and I'll show a plot, an animation in my slides in a minute, we talked about this, the formation of this BAO peak in the galaxy two-point correlation function. And the way you measure this is by looking at galaxy clusters. And so you get this delta function for your transforming into these wiggles. Okay? So this is a summary of the last talk, just in case things were not clear enough. And you can update your notes if you want. All right, so let me move to the slides. So there are a lot of topics I can cover today. I think you're gonna see that even just from these conclusions that we had here in our talk, and the first talk I gave on Sunday, I hope you will feel that you can actually make all kinds of considerations yourselves just by thinking of a model and thinking about the potential signatures it may have in the different observables. Okay, so to sum up what we had before, precision cosmology, there was tremendous progress over the last few decades. So this is the CMB temperature, measured to great accuracy by the first satellite to measure the CMB anisotropies, but COBE also could measure the temperature itself. So it measured the 2.726 and also the anisotropies on scales of roughly 7 degrees. So this was not enough yet to see even the first peak in the oscillations. Then WMAP 10 years afterwards and Planck 10 years after that have detected the power spectrum with great accuracy. We'll see in a minute. I remind you that the CMB fluctuations, we take the map, we decompose into spherical harmonics, and we look at delta t or delta t over t. We take the power spectrum, and that gives us, since these perturbations are to a very good approximation Gaussian, that gives us all the information here is encoded in these CLs, which you can plot as a function of L here, and this is the famous plot that we've been looking at. The acoustic oscillations, the basic physics is always a driven harmonic oscillator. The driving force is generated by the dark matter, which dominates the potential wells. And the restoring force is due to the radiation pressure. And the baryon mass enhances the peak ratios and also causes the damping, okay? The exponential damping. Okay, so we saw this. Just to give you a feeling for how how the CMB power spectrum depends on changing the baryons, for example, or the baryon energy density or the cold dark matter energy density. This is sort of the way this looks. You can see here the peak ratios change drastically as you change this, and here the whole thing shifts up or down. This is the potential envelope effect that we talked about.
It looks like the peak ratios change in both.
Yes, because it's more it's a little more convolved than what I showed you. But the main effect is this. Equal to 1, and then yeah, when you increase one, you decrease the other. That's correct. Yes, that's why. Okay, so these are the Planck measurements. What you can do here, you can fit for the energy density in matter, in baryons, and you can also get H0, as we talked about. You can also get these other parameters. NS and AS have to do with the primordial fluctuations that we didn't talk about. We assumed they were given to us by inflation. And I didn't talk about tau, but let's leave that out. Okay, so now let's talk about H0. So with H0, there's also some history of measurements. This goes back to the 1950s, even before that. So I skipped the measurement by Hubble, which was an order of magnitude off. It was something like 600 kilometers per second per megaparsec, according to his observation. So you can see measurements have been improving, but really, even more than 10 years ago, the spread of measurements was huge compared to the range that we are interested in now, which is sort of between 67 and 80 or so. This is how this evolved over the past. This is how the Hubble. There's supposed to be some shading. The color is not showing in the projector. But these are the CMB measurements and the way they've evolved. And these are the local distance ladder measurements. And you can see that the tension starts at around 2012 or 2013. These start to deviate from one another. Okay, so that's when the tension started, and it's been growing. So this plot only uses Schu's results up to 2016. But if you include the updated Schu's results, where every time you improve the Cepheid calibration, you include more supernovae, et cetera, this is how this is evolving. I plotted it here as a function of the tension in sigma with the CMB results as a function of time. And then you can think of extrapolating this in different ways according to how optimistic you are about or pessimistic you are about this being a true anomaly. So this is what you would think would happen. If you look at the most recent measurements, and this is a plot where most of these entries, or a lot of these entries, only came in over this past summer. Okay, so this H0 tension is sort of becoming a crisis because the tension now, if you consider the late universe measurements, which come from the local distance ladder where the supernovae luminosities, the distance to the supernovae luminosities is calibrated via Cepheids, like we talked about yesterday, or via other types of stars that we can use as standard candles, like tip of the red giant branch stars or Miras stars. So these are all distances to supernovae, just with different calibrations. This is the lensing time delay from quasars that I talked about. These are other two more methods that I won't discuss. But you can see that all the late universe measurements are around here, while the early universe measurements, one relies solely on Planck. So we discussed how you can extract H0 from Planck. And one is via this alternate route where you don't use the anisotropies in Planck at all. You use BBN to infer the energy density in baryons from the sensitivity of the deuterium abundance to the photon to baryon ratio. And then you use DES, which is a galaxy survey, from which you can extract weak lensing, the weak lensing effect, which has to do with the energy density in dark matter. So you can do this, and you get more or less a similar value. But this also relies on early universe physics because the BBN is affected by what happens very early. Anyway, if you combine these measurements and you calculate the tension, depending on which combinations you take, you're hovering around 5 sigma now. It's become a custom in cosmology conferences lately to poll the audience sometime during the conference and ask them what they think about the Hubble situation, the H0 situation. Is it a tension? Is it a crisis? And more people are now moving from tension to crisis. So most people are somewhere between a tension and a crisis. Okay, that's not very important. We ended yesterday's talk with this plot and the realization that really the tension is not, because of the important input from BAO, where you're not measuring H0 or the co-moving sound horizon at radiation drag or at recombination. They're very similar. I mentioned that yesterday. If you take into account this input from BAO, you see that it's not so easy not necessarily easy to reconcile this tension. So here I'm showing what the shoes, not I'm showing, this is taken from this paper that I gave you as a reference, the Hubble Hunter's Guide by Lloyd Knox and Marius Milea. So here is the range of uncertainty of the shoes measurement, the local distance ladder. So somewhere hovering around 74 for H0. But it's a direct measurement of H0, so it has nothing to do with RS drag. And then Planck is here. From Planck you can get RS drag and you can infer H0. So this is Planck, the tiny blue circle here. BAO forces you to go along this green line, okay? And you can already see from this that by trying to play with some parameters, like, for example, like the energy density in dark matter, what this does to the Planck data is it moves the Planck best fit value along this axis. But this is exactly perpendicular to what BAO forces you to do. Okay, so this is not a good way to solve the tension. And this shows you that you really need to take into account all the measurements, all the relevant measurements, if you want to think of a solution that will actually work. Okay? The reason there are these large ellipses here is that there's also a lingering tension in Planck data that hasn't been resolved even with more data and improved analysis. If you take the Planck data and you only look at the sort of the larger multiples, the ones above 800, these are the ones where Planck could go beyond WMAP. WMAP did not have the resolution to go beyond L of 800 or so. So if you take only L of larger than 800, this is actually the best fit. If you take only L smaller than 800, which agrees where you agree with WMAP, you get this fit. Okay. So this has to do also with omega matter, but again, it doesn't seem that this disagreement necessarily helps you solve the Hubble tension. Low E is low L E-mode polarization, but I didn't talk about polarization, so let's leave that out. Okay, so now what are the ideas we can think of how to solve this tension? So what's important is to realize that if you look at the contribution to these scales that we measure very well from the CMB, both the damping scale, which has to do with the baryons, and the sound horizon scale, if you take into which depends on both, if you look at the contribution to them, the accumulated contribution to them over time, you see that most of the buildup of this sound horizon happens in the decade in redshift before recombination. Okay, so if you want to try to affect these things, and you have to change them by about 7% if you want to resolve the tension, you have to do something around here, around these redshifts. Okay, and two proposed solutions are also plotted on this plot. One of them is just to increase the number of effective degrees of freedom. Did Josh talk about ineffective at all in the talk? earlier today? Okay, so you know something about this. So for example, you can add a species of neutrinos or something like that. If you do that, it seems to sort of magically solve at least the problem of getting a larger H0. I'll get back to that in a second. Another option is to sort of invoke, in this paper and other papers, invoke a new form of dark energy, an early dark energy component, which has to somehow miraculously show up here, add some expansion, and then immediately fall off. Okay, so this is very fine-tuned. It works if you fine-tune it, but it's not very well motivated, and it also causes tension with other measurements. But I don't want to get into that because the sort of phenomenology here is not necessarily interesting for this audience. But let's focus more on this this neutrino idea. So maybe extra neutrinos. Maybe that's the way to go. So if you look at Planck data, and you look at this is taken from the Planck 2018 Cosmological Parameters paper. I didn't put the reference, but that's really fresh. It's from about a year ago. So this is the two-dimensional fit of N effective versus H0. So you can see that if you increase N effective, you increase H0. You can also see another parameter showing up here, which is sigma 8. Some people here in the audience asked me what sigma 8 was. So let me just mention what that is. Sigma 8 is a measurement of the amplitude of the power spectrum, averaged over a region of about 8 megaparsecs in size. That's a scale of an inverse 8 inverse megaparsecs is the scale that matches the size of a cluster, a galaxy cluster. And on these scales, the CMB is sensitive, and we can actually extract sigma 8 from that. You would think that the CMB would have no information about clusters because clusters form much later. But you have to remember that we are not observing the CMB at 1100, we are observing the CMB today. And as the photons travel towards us from the last scattering surface, sometimes they do interact. For example, photons that pass through galaxy clusters can interact with the electrons that are traveling in the galaxy cluster. And there are two effects here. This is called the Zunyaev-Zeldovich effect, the effect of inverse Compton scattering of photons from the CMB traveling through galaxy clusters and interacting with the electrons. There's a thermal effect, which has to do with the fact that electrons have higher temperature here. And there's also a kinetic effect, which has to do with the fact that the electrons have a large dispersion velocity in the cluster. So they have high velocities, and that also can scatter off the photons. And this there are ways to take the CMB data and infer from that the SZ effect and measure in that way the amplitude of power spectrum, the power spectrum on cluster scales. Okay. Yeah.
When you show those CMB, does it talk about a phase to all L, high and low, just high, just low?
This one? This one, yeah. I think this is all L. This is the whole, all Planck data, yeah, in this case, yes. Okay, now what you need to remember is that as you try to play around with H0, omega matter, and N effective, you always have to reconcile the CMB and the BAO information. And for example, BAO doesn't like the fact that you want to increase N effective. So this doesn't really help. Just increasing N effective, even though in the last plot you saw that just setting N effective to 4 sort of helps, and you can see it here. You increase N effective, and you tend to increase the Hubble parameter. So as long as you're still in agreement with the constraints on sigma 8, when here you're still sort of in agreement, if you go in this direction, this is not allowed by BAO. So what else can you do? So this is an animation showing the evolution of perturbations, the same thing I plotted on the blackboard yesterday. So you see the BAO scale forming here. Let's look at it again. I hope it should start again. Because the perturbations are adiabatic, they all start at the same spot. Blue is gas. Blue is the baryon gas. Red is the photons. They travel together until the photons decouple and go down. Let's look at it again. We'll look at it a couple of times. Every time this plays, you can sort of stare at a different component. So this is the tightly coupled fluid moving around, and then the photons decouple. Okay. Now look at neutrinos. Look at what happens to neutrinos. Again, when it plays again, as the perturbations move out, stream out of the peak. Look at neutrinos. They're traveling faster than this tightly coupled fluid. Because of the baryon effect on the photons, it slows them down, and then neutrinos travel even faster. Okay, but they also, if you look at the effect of neutrinos, so this is a snapshot of this in a moment, taken in some moment of this film here, and it's taken from this paper by Francis Jan and Chris Sigurdsson, Francis Jan Siracine and Chris Sigurdsson. Here you can see the effect of the neutrinos. Okay, so if you have photons and taking into account the neutrinos, you have this green line here. Okay, that's what would happen. If you somehow remove the effect of the neutrinos, you see that the photons would be somewhere here. Okay, and there's also you have to remember that there's some kind of difference between the photons and the baryons. You can barely see it here, but there's a little difference between them here, because they already start to decouple a little bit. But if you include the neutrinos, they cause this this separation to be even larger. So we said that just adding neutrinos doesn't help. But what if you add self-interacting neutrinos? So you add neutrinos which have a self-interaction. This self-interaction does not allow them to propagate as fast as they would if they were completely free-streaming with no interaction between them. And so if you do that, then if you take the self-interacting neutrinos and photons with self-interacting neutrinos, they both would be here, and you would remove this effect on the photons. Okay? So seeing it differently, if you add self-interacting neutrinos, what would happen to the CMB power spectrum that we spent some time looking at? Notice here this x-axis is plotted linearly, so it's not the way, usually when I plot it, I plot a log-log plot. Okay, so you're used to seeing the first peak very, very large, but here we're already at 500 here. Okay, so these are the small peaks. You can see that if you take LambdaCDM, so this is the line. What I'm showing here is the deviation from LambdaCDM. Okay, so for LambdaCDM, the deviation is 0. Okay, that's the black line. If I add another species of neutrinos, what happens is that the perturbations are suppressed. Okay, this is because of the effect that we just saw before, that the neutrinos cause the photons to separate a little bit more from the baryons, and this decreases the amplitude of the power spectrum. But if I then invoke an interaction between the neutrinos, a self-interaction between the neutrinos, and say I still leave the number of effective neutrinos at 3, this self-interaction would increase the power spectrum, okay? Because it would add to this tightly coupled baryon photon fluid, and it would make everything larger. If I do both, if I induce this self-interaction between the neutrinos and also increase the number of effective neutrinos, then I sort of cancel out these two effects and I get this dashed line. And so it sort of seems to work. And because adding this extra relativistic degree of freedom helps you increase H0, this is sort of a solution to the problem. The only problem with this solution is that the coupling that you need for the self-interacting neutrinos is something like the order of 10 to the 10 G Fermi. So it's kind of strange, okay, to invoke such a strong self-interaction between neutrinos. So this, this audience should not like this solution very much, although phenomenologically, when we talk about the effects on the CMB, it sort of is able to do everything we want to do. So not spoil anything, but still help solve the H0 tension. Yeah. So here it's between all of them. Yeah. Otherwise, otherwise you're not adding. Yeah. Okay. Yeah.
How well do we understand the breaking of the degeneracy between in the ineffective H0 flat direction? What is the reason that the degeneracy is not totally flat? When you showed the ineffective versus H0, it closed the contour at some point. What is
the closing of the contour is just a 1 sigma and 2 sigma uncertainty.
But in that flat direction, what breaks the degeneracy? Do we have a clear understanding from the power spectrum point of view?
once there are a lot of effects that happen once you do this. Once you induce add this effect, so you can't add you can't increase an effective as much as you want. At some point, you're going to ruin the fit completely. So that's why the ellipses end. Why there's a degeneracy is because they both affect the same things. I mean, the way H naught goes is related to this. We saw this is through the potential envelope in rho m, and that's degenerate with the effect of an effective.
I guess my question. Okay, I should sharpen my question. What I'm confused with is that whether that degeneracy is broken by the damping tail change, or is because of the perturbation on the perturbation level.
Broken by the damping tail. Why the damping tail?
Because if you have more effective, you actually increase the damping scale and you have more peaks to be suppressed.
Yeah. Okay.
I mean
that's the effect, right? And then.
But that was like. I mean, we can chat about this later.
I mean, but okay. But you're right. It's all these competing effects. Okay. But it's complicated, and there are other effects that I did not, cover in the sort of simple explanation that I gave you before, and so this is supposed to give you a qualitative understanding of this, not a complete understanding. Yeah.
Can you give us physical intuition for what does the neutrinos interaction do? I mean, I understand that it stops running of the power spectrum neutrino, but I don't really understand what it does, because we don't have many neutrinos. Like in terms of energy density, neutrinos is not huge. So I don't really understand.
It's not huge, but it is enough to affect there are part of the budget, and so it is enough to. So the fact that they stream out they do have an effect on the photons. That's what you saw in those plots before. You saw that when you have the free streaming neutrinos, they pull on the photons a little bit, and cause the photons to decouple from the baryons a little bit earlier. But it's another radiation species, you see. So that's why.
I think it's really involved with the sound speed of the.
Mm-hmm. That's right. It affects the sound speed. That's right.
Right.
Mm-hmm.
Just think about the
It affects the sound speed. So what we saw before, we only talked about what affects in affecting the sound speed. We only talked about rho baryon and rho gamma, but rho the neutrinos also enter there. Okay. So that's yeah.
I'm confused again.
Let's talk about it later, because I don't know if we're going to solve this. All right. Okay. So what is the prognosis? So we have this full history now. We used to have this large scatter, and now, thanks to the latest measurements, we are really zooming into this small region here, and we have this tension between the early universe measurements and the late universe measurements. So I sort of flipped rotated this figure that you saw before, and this tension is increasing over 5 sigma. So we need new ways to probe this. Okay, so again, this is a tension between the late universe and the early universe. So what other ways do we have to try to probe this this huge volume over which something seems to be changing? It doesn't seem that if we take the cosmological model and assume that it holds as LambdaCDM throughout this evolution, that everything works. Okay, so where to look next? This brings us to the question of where to look next. So I touched on this a little bit yesterday in the session that we had, in the conversation that we had in the afternoon. So a good figure of merit of where to look is the number of modes that we can access. This is because constraints on parameters usually scale as the inverse of the square root of the number of modes. So from the CMB, if you count the pixels in a map, the number of pixels just goes as 2 times L max squared, where L max is the maximum L that you can actually measure before the damping scale affects you too much. And that's about 10 to the 7. Okay, that gives you about 10 to the 7 modes. And with the temperature, we're almost done. Because of the damping, because of the cosmic variance, there's not much to look at. If you increase your resolution and you're able to probe a larger L, you're not going to get much because of the damping. So what's left? One thing that's left is polarization. So the CMB radiation is polarized. You can decompose the polarization field into a gradient component and the curl component, similar to what you can do with an electromagnetic field. These B modes, the gradient and curl modes are called, like for an electromagnetic field, they're called E modes and B modes. The B modes are a particularly interesting signature of inflation because they can only be created by tensor fluctuations generated in inflation. But this will have to leave for another time. So I was planning originally to talk a little bit about this, but I'm not going to. You can see a review of mine with Mark Kamenkowski from a few years ago. This is a pedagogical review in annual reviews of astronomy and astrophysics, which sort of covers this whole topic. So I refer you to that. I'm not going to talk about this at all. Okay, but what happens after recombination? So after a recombination, we saw in the first talk that we can access the 21 centimeter signal. We saw that it had to do with a hyperfine transition in the hydrogen atom. And the one advantage of this is that now we are not talking about things that happen in the radiation, which are affected by the gene scale, by the corresponding gene scale. Now the gene scale is much smaller. So we can probe things up to much, much larger L's. Okay, so in principle, if we can access the information in the dark ages, for example, which are clean in terms of not being affected by any astrophysical processes because stars have not formed yet, but we saw that there is still an effect there. Remember that the spin temperature decoupled from the CMB and followed the baryons for a little while during the dark ages between redshift of 200 and redshift 30. So that's one epoch where you can look at. And then there's again an epoch where you can look at this, which is reionization. And between them, what we talked about, so here I'm showing an animation that goes from redshift 30 to redshift 7. And here I'm showing the 21 centimeter signal. You can see that it starts going negative. This is around the time, redshift of 17 or so, where edges made their measurement. This is the minimum of the signal because the spin temperature through the Lyman alpha flux of coming out of stars follows the baryon gas. But then stars die, black holes form, they radiate X-rays, and they heat up the gas and the spin temperature with it, and then you get an emission signal, a positive signal in 21 centimeter. But then at some point, all the neutral hydrogen is ionized. The universe is completely ionized at the end of reionization, redshift 7, so the signal goes away. Okay, so this was the picture of the signal that we saw. And this brings us to this interesting epoch where the signal is at its minimum, which is cosmic dawn. And so in these three epochs, you can hope to see the 21 centimeter signal as an example. So as I said, fluctuations extend to much, much smaller scales because the gene scale only matters on much, much smaller scales. So you can get something like 10 to the 6 modes. And you can also tune the frequency that you're measuring at. If you're tuning the frequency, you're measuring a different redshift, okay? Because it's always 21 centimeter radiation at the source. But if you're changing your observing frequency, you're measuring it at different redshifts. So you can actually measure something like 10 to the 4 independent redshift slices. So if you combine this, you take this squared and multiply by this, you get something like 10 to the 16 modes, okay? So the potential here is much, much, much larger than with what we had for the CMB. The only problem is that this is swamped by foregrounds. And some of the signal is blocked by the ionosphere if you try to measure it from Earth. So you have to really, if you want to actually access this number of modes, what you would have to do is you would have to take the far side of the moon, which is not affected by terrestrial radio frequency interference, radio transmission interference. But if you cover the far side of the moon with interferometers and you cover a very big chunk of it, then you can hope to reach something like this number of modes. It sounds funny, but there are ideas for how to do this. You deploy robots there, and they sort of take aluminum foils and spread them around, and these form the antennas that you need to in order to measure this signal. People are actually thinking about this. Sorry?
Would anyone pay for such a project?
So one argument I've heard is that if you think of the space station, for example, the International Space Station, and you think of the AMS, I don't know if you've heard of the AMS experiment, the cosmic ray experiment led by Sam Ting on the AMS. The cost of that experiment relative to the cost of the space station, if you take that, and then you think of a lunar base that some governments are thinking of building, and you take the same ratio of the cost of the lunar base and the cost of these robots that would take these aluminum foils and spread them out on the far side of the moon, the ratio is about the same. So it shows you that if such a large-scale project is in the end funded by some government, then it might be realistic that they would, as part of that, they would also fund some kind of science experiment. And so if we can convince the governments that this is really where we need to go, then maybe they'll do it. But that's the most optimistic argument I've heard about this. Okay, so cosmic dawn we talked about. This signal has to do with the formation of the first stars and galaxies, the light that they shine, the Lyman alpha flux that they shine that couples the spin temperature to the baryons. And so the spin temperature deviates from the CMB, and then you have a 21 centimeter signal that you can observe. The reason it's a very nice epoch to look at is that it's the coldest moment in the universe, in the history of the universe. Okay, the coldest moment in the history of the universe is right here, right after the formation of the first stars. Before the remnants of the first stars start to heat up the universe, it had cooled down after recombination to the minimum point, and from then on it heats up, and it never goes back to that coldest moment. And since dark matter is cold, any heat exchange interaction between the dark matter fluid and the baryons, you might hope to be able to see in the coldest moment. Okay, so that's sort of an argument, a motivating argument to look, if you're interested in dark matter, to look at this epoch. And we talked a lot about the 21 centimeter global signal, so the average temperature on the sky, but there are also the fluctuations, the spectrum of fluctuations that you can measure, and that will encode more information. Okay. And then there's the epoch of reionization. Here you really have to separate the cosmology from the astrophysics because a lot is going on, you still cannot detect sources from here. It's not close enough to us to be able to detect many individual sources here. So what you have to do is employ a technique called intensity mapping, and let's talk about intensity mapping for a minute. So this is sort of a plot that shows you why intensity mapping is a powerful technique. So on the left side, I'm showing a galaxy distribution. So this is just galaxies distributed in a patch of sky of something like 2.5 degrees by 2.5 degrees. And in red, I'm showing the galaxies which emit CO. So photons from rotational transitions in the CO molecule, and the flux of CO is large enough that the VLA, the Very Large Array Telescope, which is a very, very expensive telescope, can detect in about 4,500 hours. Okay, so if you take VLA, you waste 4,500 hours, which is a lot. It's about a season of observations. You devote the whole season for this small patch of sky, you would be able to detect only these red galaxies. Okay? But if instead of trying to detect individual galaxies, you just tune the frequency of your observing telescope to measure all the photons that come in with the corresponding with the frequency corresponding to CO emitted from this redshift slice, you can cover the same field with an experiment that is a fraction of the cost of the VLA, and you can actually get with much lower resolution, you can get emission from the whole field. Okay, so you can see that there's some correlation between these red galaxies and this here, but there's information here that you cannot access or infer from only looking at the red galaxies. And again, you will never observe even these red galaxies because you'll never have this telescope time to do this. But you can do this. Okay, this is a cheap way of getting low resolution maps of some redshift slice. And then you can take that redshift slice, you can change your observing frequency and measure many different slices. Okay, and this is just in CO emission. So some emission from a particular molecule. You can take another molecule which has some rest frame or some atom which has some emission that is sourced by star formation or is caused by star formation, so it happens a lot in the history of the universe. And you can again tune your frequency, change your frequency, and get these maps that will fill in the volume. So this method is called line intensity mapping. We wrote a review about this method a few years ago. And I encourage you to look at that as well, because this method will provide you information with which you can have a lot more statistics, first of all, probe a region in the history of the universe that cannot be probed by other methods, and also it will have distinct sensitivities to particular models, but that's not a general thing. So just to demonstrate how this can relate to the H-naught tension, the challenge when you do something like this intensity mapping work is that if you observe these epochs here with this method, you have to take out the effect. You're affected by all the astrophysics that happens here. Okay, and that's hard to model. What is the star formation rate history throughout the universe? What happens to the gas, and what happens to feedback between star formation and the gas in galaxies, and so on and so forth. So there's a lot of structure, and you have to sort of clean that out. What you would want is a measurement like this. What you want is to get to the underlying density fluctuations. Okay, this is, as people who want to study fundamental physics, this is what we are actually interested in extracting. So if we can do this, if we can distinguish between the astrophysics and the cosmology, then can line intensity mapping weigh in on the Hubble tension? So this is a demonstration of how it can do that. So if you try to reconstruct the expansion history in a model-independent way, so you don't assume LambdaCDM, you just take the measurements that you have. Okay, so you start from the local distance ladder, and then you add to it. You take the shoes measurement, you add to it BAO, and you try to sort of go forward in redshift. All your measurements, all your data information is coming from here. So the shoes information ends here. Then BAO allows you to get a little bit further away, because you can observe galaxies in large numbers and extract the BAO scale up to redshifts between 1 and 2. But then you completely lose control over what happens at higher redshifts. So if I zoom in here, this is the region where you completely lose control. But if you add this information from intensity mapping, and this is taking into account forecasted sensitivities for upcoming experiments, and this is a realistic estimate for what you can do, you can see that you can sort of try to constrain the evolution of the Hubble parameter as a function of redshift all the way to reionization or so. Okay? So if anything funny happens in between the CMB and today, we'll be able to constrain it with this method. Yeah. You don't do it model independently. Well, you're asking model independently in terms of the correlation between H0 and RS drag, or are you asking model independently in terms of the astrophysics?
No, not astrophysics. I'm asking about.
So it's the same. So it's the same BAO measurements that you get from the galaxies, from surveys of galaxies, that you can do with. You're doing BAO measurements with line intensity mapping. So this is intensity mapping BAO. And so it's the same. It's just something you can do at much higher redshifts, because galaxies you can only observe in large enough numbers up to redshift 2 or so. You can never do that at redshift 3 or 4 or 5. But with this method that I just discussed, because you're measuring all the photons that come in, you can actually get maps at this high redshift, and then you can do the same BAO analysis. But it's similar to the analysis that you do for galaxies. It's not, in that sense, it's not different. The challenge is to separate the astrophysics from the cosmology, but that can be done, at least to some level. So there are ways to do that, and they're discussed in this paper, for example. Okay, so where to look next? Then we have galaxies, okay? And just to give you a flavor of how many galaxies do we actually have to observe if we want to compete in terms of the number of modes with the CMB or with intensity mapping. So can we beat the CMB? That's the question. So imagine you take your measurement of some volume, galaxies over some volume, and you divide this into voxels. Okay, so these voxels have a size r, small r. The width r is set by the maximum linear scale. On very small scales, structure formation becomes nonlinear. And it's, I described everything at the CMB, things were simpler. But as we go to smaller and smaller redshift, the evolution of perturbations becomes very highly nonlinear, and it's hard to calculate even theoretically. So you're limited by the maximum linear scale. And of course, the problem gets worse as you move to lower redshifts because things go into the nonlinear regime earlier in terms of the scales that as you go to smaller and smaller scales. So already larger scales are in the nonlinear regime. That's what I mean. Okay, because perturbations grow hierarchically. So if you think of the number of galaxy modes that you get, it's sort of equal to the number of voxels. And that's given by just dividing this this larger dimension by the smaller dimension. This goes as the volume that you're measuring times k max cubed over pi cubed from this relation here. And now the key here is that if you go to higher redshifts, you increase the volume that you're measuring, and you're also taking k max to larger values. Okay, because the transition to the nonlinear regime happens on smaller and smaller scales as you go back. Okay, and so you can do this, and you actually get, if you can measure galaxies up to redshift 3, 4, 5 instead of only just up to 1, you get a factor of something like 10 to the 3 gain in the number of modes in from galaxies. Now, how many sources do you actually need? What you need is what you do at the end of the day is in each voxel you have some number of galaxies, okay? And what you want to do is you want to measure the density fluctuations. So if you want to beat the shot noise, because this is a discrete measurement, you need to have you need the variance to be smaller than at least I don't know, a few tens of percents or a few percent or so. So to beat the CMB, what you actually need is a total number of sources such that the number of voxels times the number of sources per voxel. This you need to have at least 10 sources per voxel or so. So the central limit theorem holds. And then the number of voxels we saw is equal to the number of galaxy modes. So you can see here that if you want something large, better than the CMB, which had a number of modes of about 10 to the 7, you have to observe more than 100 million galaxies. Okay, so that's the ballpark number that you want to get. If you want to beat the CMB, you need more than hundreds of millions of galaxies. This sounds fantastic, but upcoming experiments like Euclid and LSST, both will start taking data in a few years, are targeting something like 1 billion sources each. Okay, so they're not actually doing it with spectroscopy, so they're not actually going to have a redshift for each of these sources, but they are crossing into the regime where, at least in principle, we are talking about a competitive observable compared to the CMB. Okay, and
why do you need a measurement of the redshift of these sources?
Because if you don't know where they are, then you don't know which voxel to assign to them.
So you need the distance from them.
Yeah, but you're measuring redshifts. I mean, you can measure redshifts in principle, but if you're just putting a telescope on, pointing a telescope to some patch of sky, you see lots of light sources. But if you can't take only if you can take the spectrum of each galaxy, then you have the spectrum and you have absorption lines, and by seeing how much they shift, you can measure the redshifts. But if you're just measuring the light and you don't have a spectrum over each galaxy, then it's hard to tell where they are, how far they are from you.
You use the redshift to find the distance from the galaxy?
The redshift is a measurement of you don't have to infer the distance. You can't infer the distance. I mean, that's going back to the standard candles and all that. But what you normally do is in redshift space, you calculate the power spectrum, or you split into voxels. But you need the redshift. What I'm saying is that even getting the redshift is not something that actually these experiments will do. So there's a way. There are ways to get sort of an estimate of the redshift even without taking a spectrum. But this is going well into astrophysics and observation. So. Let's not go.
Will you not be able to use this 10 to the 9 galaxy that's going to be?
So you will be able to use them only with larger errors than you could if you knew the redshift. So what you do is you take measurements in different frequencies, and even if you take the measurement in 4 frequencies or so, there's a way to, through the behavior of the signal as a function of these frequency bins. These are called color bands. You can do what's called photometry and estimate the redshift. But this is not the exact redshifts like you get if you actually take the spectrum of the galaxy. then from the absorption lines, you get a very good measurement of the redshift. Okay. So what about the nearby universe? So there's not a lot of modes in the nearby universe. The 3D space is limited, but maybe you can go to the time dimension. So this I mentioned also yesterday afternoon. You can think of things that are like explosions, like gravitational waves from coalescing compact objects, fast radio bursts, tidal disruption events, gamma ray bursts, supernovae. I'm going to talk about fast radio bursts if I have time a little bit later. And all these can be unique probes of both dark matter and dark energy, and some of them can actually be seen to even high redshifts. Okay, so there's also some promise here in looking at transients. Okay, so in what's left of the time for this talk, I'm going to talk about some prospects of multi-messenger cosmology. Okay, so here I'm showing you all of these different observables that now we already know something about. So we talked a little bit about supernovae. This is sort of an illustration of the BAO scale. So from every point here, there's sort of a ring around it where you should see more galaxies. This is because of the Baryon acoustic oscillation scale. This is intensity mapping, CMB, and these are secondary anisotropies. So I talked about the Zunyab-Zeldovich effect. From scattering in clusters, and there's also the lensing effect that happens as photons travel through a dark matter distribution. They are deflected, and you can try to measure from the CMB that you measure, you can try to infer the dark matter distribution, the projected dark matter distribution from the statistics of the CMB. There are ways to do that. Okay, so how much time do I have? Half hour? Okay. So let's try to make contact with Josh's talk and with things that we already discussed a little bit this week, even in my talks, and talk about the dark matter landscape. Okay, so I think Josh plotted something like this in his first talk, and this is to orient you. This is where WIMPs are. Up here, there are models that you no longer have particles. You're way beyond the Planck mass, but you can have dark matter hiding in the form of some things like primordial black holes. Below this scale, you're in fuzzy dark matter. That's where the de Broglie wavelength of the particles is comparable to the size of galaxies already. So you cannot, or dark matter halos. So you cannot form the structure. So you can't go below this. And here is where sort of the hidden sector dark matter lies, and this is where ultra light dark matter, bosonic dark matter lies. And this is stolen from this Cosmic Visions report, which was written after following some 2 years ago. There was a conference discussing all kinds of methods, even with small experiments, to try to probe models beyond the WIMP. And what I've been trying to motivate is that with cosmology, you can actually gain access to all kinds of cosmological phenomenology can help you test all kinds of models beyond WIMPs. So let's go back to the edges detection that we talked about on Sunday and see how to actually check if the dark matter explanation to the edges anomaly is viable. We need to take into account all kinds of cosmological constraints coming from all kinds of different processes. Okay, so what edges measured was this. Okay, this doesn't look like what I plotted, but this is what it actually measured. This is because the foregrounds are so large. The signal was in millikelvin, I remind you. This is in Kelvin. So what edges actually measured is between 50 to 100 megahertz. It measured something that looks smooth like this and of order 3,000 Kelvin. But this is dominated by galactic synchrotron emission. So what it did is it tried to fit a polynomial to this, remove the foreground signal, and be left with some kind of noise. Okay, hopefully just noise. If there's nothing here except for foregrounds, then this should be smooth noise with a small root mean square error. But you see that it had these features. Okay, so what it did next is it tried to, in addition to fitting for foregrounds, a smooth component, it tried adding this best fit 21 centimeter model, and I told you that the model was very strange. It had this flatness feature here and the sharp transitions here and here. So I tried to fit that as well. Notice here we are in 500 millikelvin, and we're adding this fit to something that is measured at 3000 Kelvin. But still, when you add this to the polynomial fit, you get residuals that look like this. Okay? So from the fact that the residuals improve a lot when you include this fit, they deduced that they actually measured this signal. And just to orient you, remember we said that because the spin temperature cannot go below the baryon temperature, there's a minimum that we cannot go below with LambdaCDM, and that's around 200 millikelvin or so, and this is already in about 4 sigma tension with what edges measure. Okay?
Sorry, in the
Yeah.
residual plot, do you remember how large the error bar is?
Here.
No, I mean the error bar. Like
What error bar?
for the residual plot, when you compare it with the data, you compare with the size of the error bar. So that shows how good the fit really is. I mean, if the error bar is huge, then I can even say that B plot.
So when you include, when you fit and subtract the foreground model and the signal, this is what you're left with.
Right.
Instead of 0, you're left with the root mean square error of something like 25 Kelvin. And this is better than 87 millikelvin that you get if you don't include. This is 87 and this is 25.
Sorry.
So this is how much this improves. Okay? By adding this, you go from 87 millikelvin root mean square error left over to this. Okay? So this is sort of the reason they think they measured this. Okay? So this is the tension that we're trying to explain. And this goes back to now I want to motivate dark matter baryon scattering in general. Okay? So if you think of direct detection experiments, and you're going to hear several talks about them, I don't know if you can see anything from here, but what you want to see is that these are limits on the WIMP nucleon cross-section as a function of the WIMP mass, okay, with all kinds of different direct detection experiments. You're going to hear a lot about these next week. But you see that they all have this wall at around 10 GeV or so, okay, because at masses per dark matter particle lower than this, the recoil on the heavy nucleons is not enough so that you can actually measure something. And now, again, consider a general cross-section parameterized as some power law of the velocity, the relative velocity between the dark matter particle and the baryon that it's scattering off from. Cosmology is sensitive to this, and it doesn't care about the mass. Okay, so how would this turn up? Show up. So now I can actually show you this. I couldn't show you the CMB constraints on Sunday because we hadn't talked about the CMB yet. But now you already have enough understanding to be able to think of what the effects would be on the CMB power spectrum by adding an interaction between dark matter and baryons. And what you actually see here is that you would have an enhancement of the first peak. You would have increased small scale suppression, and you will shift the peaks a little bit. Okay. So an exercise for you is to think of why all of these effects happen. This is the baryon loading effect that I talked about. The small scale suppression is because and the Doppler shift is because of the effect on the speed of sound, which is now different once you can exchange momentum via this interaction as well. But that's where it's coming from. But this is, of course, sensitive to masses well below a GeV. Okay. The point is that the CMB becomes less and less sensitive as the power here, the power of the dependence on the velocity, as the power goes smaller and smaller. Because as you take n to be smaller, say you take n to be -4. Okay, so I touched on this a little bit. If you take it to be -4, then the interaction is much stronger when the velocities are smaller. And because all of the temperatures drop, so if I start from 1100 and if I look at the CMB temperature, okay, as a function of redshift, it drops, okay? And the same happens for the baryons. They both cool down. The relative velocities of these particles is much lower at the time of cosmic dawn, for example, where the edges signal is measured compared to recombination. So perhaps you can evade the constraints that you have here from the CMB, from the power spectrum of the CMB, which is measured very well. Perhaps you can evade them by having sigma naught low enough. But then because V goes down with time, the interaction will become very important here at cosmic dawn. Okay? So that was the idea behind thinking of dark matter baryons scattering with this sort of potential, this sort of interaction, which is just a Rutherford interaction. And maybe that can have an effect on the 21 centimeter signal. So specifically, a model of dark matter millicharge. Assume dark matter has some small charge. There are limits to how large the charge can be. But if the charge is not larger than, I don't know, 10 to the minus 3, 10 to the minus 4 of the electron charge, then perhaps it can do something interesting and maybe explain the cosmic dawn signal. So how does this come about? Remember, we saw that everything about the 21 centimeter is a game of temperatures. We have the CMB temperature going down. We have the baryon temperature decoupling from the CMB because Compton scattering is no longer effective in coupling them. And then we know in LambdaCDM how the baryon temperature behaves. It just cools down adiabatically, so as a squared instead of as a. But then you add the dark matter baryon interaction. So if you look at the evolution of the dark matter, the baryon temperature, in addition to this adiabatic cooling effect here, and this Compton scattering effect that tries to couple the baryons to the photons and is only effective here, you have this extra term. So this tries to cool the baryons, this tries to heat the baryons, and now you have another effect that tries to cool down the baryons because they're losing energy into heating up the dark matter, which is much colder, okay, through the interaction. So in this way, you can cool down the baryons further if you add an interaction of the type, for example, of v to the minus 4. You can cool down the baryons further. And now the spin temperature, which is always in between the CMB and baryon temperature, now the spin temperature has more room to fall, and the signal can be lower. We can measure a lower signal, or larger absolute signal, lower minimum in the 21 centimeter temperature. Okay. But now we have to consider that there are constraints on this. So if we actually plot as a function of the dark matter particle mass and the charge, okay, and we look at the millicharge model, this is what we need in order to explain this turns out to be what you need in order to explain the edges signal. So to bring it down from minus 200, which is what you would get from the minimum you would have in LambdaCDM, to bring it down to minus 300, which starts to approach the confidence region of edges around minus 500, you need this interaction, okay? This amount of charge per mass. The question is whether this is allowed. Are there constraints in this environment? And it turns out that there are a lot of constraints from different things. This region is completely ruled out by stellar cooling. I don't want to talk about that because I'm not an expert on that, and it takes us too much into astrophysics. It's not a clean enough signal that I can describe quickly. But there are constraints mainly because the dark matter, if you can form dark matter particles inside of dense objects or hot objects like white dwarfs or red giants or so, you would cool the production of dark matter particles that then carry energy away from these objects will help them cool down and will change how fast they cool, for example. And so measurements that we can take of these objects will be different, would have been different if this sort of dark matter particle could have been formed in these objects. There's also a limit from a SLAC dark matter millicharge search. So this is an accelerator search that was devoted to searching for products of a dark matter millicharge model. Okay, so that rules out this sort of part of this 2D plot. And then there's a huge region of here that is ruled out only using one event. Okay, this one event is the 1987 supernovae that was detected in the LMC, the Large Magellanic Cloud. It is close enough to us. It's really in the local group. It's even closer than some parts of our galaxy, closer to us than some parts of our galaxy. This is close enough that we can actually measure the neutrino flux coming from this supernovae. Now, back then, this is many years ago. Now it's even 33 years ago. Back then, we didn't have very precise measurement experiments that could measure the neutrino flux, but we did have several online. And this is the measurement. So it's about these are individual neutrinos that were measured from supernovae, and the total number here is about 20 neutrinos, maybe small, maybe even just 12 neutrinos. I never count, or I counted this several times, and I keep forgetting how many there are, but you can count, okay? But it's between 10 and 20 neutrinos. That's it. So how can you use 10 and 20 neutrinos to put a constraint that is this impressive on this plot, on this 2D plot? The reason you can do this, the key is the duration, okay? The duration of the signal. You can see that the neutrino flux lasted about 12 seconds, so more than 10 seconds, okay? So the whole point, the whole idea behind this constraint is similar to the stellar cooling, is that, say, you have this burst of the supernova. What normally takes out the energy, and this is some supernova modeling, I won't get into this, is the neutrinos. Okay? The neutrinos carry out something like 99% of the energy emitted in the explosion. Okay? Now assume that you can that there is such a particle, and you can create it. Okay? If you can create such a dark matter particle with a milli charge, then the dark matter particle will also carry away some of the energy. Okay? And it will cool down the supernova faster than it would otherwise. So instead of the flux from neutrinos lasting 10 seconds, it would only last 5 seconds. So it doesn't matter if you're measuring 10 or 20 or 100 or 1,000 neutrinos. Just the fact that this takes 10 seconds and not 5 seconds is enough to tell you that it's actually only neutrinos that can do this. But then the question is why does this look like this? Why does the constraint look like this? Does anyone have an idea? Why does it not extend up here or down here? That's right. So the upper bound is because if the interaction cross section, if the charge is larger, the interaction cross section is larger, then what would happen is that these chi's that are produced here would just stay trapped here because they would interact so frequently with the rest of the matter. They would not escape, so they would not help cool the supernova. And the reason it doesn't go to very small values is that if this is so small, then you wouldn't have much production of these chi particles, so you wouldn't cool the supernova again. Okay? So just one event, one supernova 33 years ago is enough to give you most of the constraints on this 2D plot. I think that's nice. And if you think of any model of any kind of dark matter particle, you'll often see this constraint from 1987A and the stellar cooling constraint. So these appear in plots of axion dark matter and all kinds of models of dark matter, dark photon, dark matter, etc.
Why is it found by low masses?
What?
Why is
This?
it cut off? Yeah.
It's not really cut off. It's just hidden behind the stellar cooling. I just put that in front.
Yeah. Not really a white region, the left, right?
This? No, it's the color of the projector. This is ruled out also. There's a constraint here and here. These are all stellar cooling constraints. This is not supposed to be white, but this projector is not the best. Yeah.
How does the self-interaction of dark matter will change the picture? Because I assume that if the self-interacting, that will also delay the cooling effect.
Yep, maybe.
But
So this is
here-
not a self-interaction dark matter model, but if you, yep. So that's exactly the sort of thing that I want you guys to start thinking about. Okay, I'm not going to talk more about this. Okay, so do I have time to talk a little bit about primordial black holes? So this is a model that Josh told me he will not talk about at all. It's not really a particle physics kind of model for dark matter, but it is a model that has been gaining a lot of attention lately. So maybe I should spend a few minutes just using this idea, and I'll tell you what the motivation is for even considering primordial black holes and why this field has been exploding so much. You probably see on the archive a lot of papers on primordial black holes, and if you've been around long enough, you know that only since 2015 or 2016 or so you have seen a lot of papers about primordial black holes as dark matter. But I'm going to use this. I'm going to focus on interesting constraints that come that we can think of for primordial black holes, which have to do with these astrophysical transients that I mentioned before. But first, for a piece of motivation. So more than 4 years ago now, I remember it as if it was really yesterday, literally. Well, not this date, because we didn't know about this date, but when the announcement came, which was a little bit later. So this was what was measured here by the LIGO experiment, the LIGO observatory, was the merger signal, or the in-spiral, merger, and ring-down signal in gravitational waves. So this is the strain as a function of time, the gravitational wave strain as a function of time, from a merger of two black holes. Okay? And there's a lot of information that you can extract from the form of this waveform. The frequency and amplitude and the time dependence. And in particular, you can infer the masses of these black holes that merged. And the measurement showed black holes that have 30 solar masses or so. This was, at the time, this was thought to be a very, very high mass for black holes that are formed from stars. Because if you want to form a black hole of 30 solar masses, you have to start from stars that are more massive than 100 solar masses, or as massive as 100 solar masses. And it's just not thought that the abundance of such stars is large enough such that the abundance of these black holes would be large enough so that you would measure these. These would be the first that you measure when you turn on the experiment. And this was literally measured when the experiment was turned on. It was not even turned on to try to detect. It was at the first the engineering run, and it was detected then. So the question that we discussed at the time was whether maybe the source for these black holes is not from stars. Maybe they are primordial. And this is not a new idea that black holes could form deep in the radiation-dominated universe. This was first suggested by people like Hawking. Hawking even there's an excerpt you can take from a paper of his. I think, it was I don't know if it was the one in 1971, but in one of his papers from around this time, he actually mentioned that primordial black holes might account for some of the missing matter that even back then was known to be a problem, that there's missing matter because of rotation curves of galaxies and et cetera, et cetera. So maybe the question that you should pose is, did LIGO detect dark matter? Okay, maybe dark matter is in the form of primordial black holes. That's why it's dark, and maybe that explains why the abundance of these black holes is large enough such that LIGO can measure them. So we can ask the question whether they are allowed to form to begin with. And so this is a plot showing you the power spectrum as a function of scale, and everything we talked about is here. Okay, so if you take into account the amplitude of the power spectrum in the CMB and the range of frequencies that you can actually access from the CMB, this is what you can access, this tiny little piece here. Okay, these scales correspond to horizon mass scales, and primordial black holes can form if the perturbations are large enough, of order unity or so, inside the horizon. Then they would collapse. Then that horizon size would collapse and form a black hole. So with the CMB, you're only sensitive to. You're barely not sensitive. You're basically not sensitive at all to any of the scales that correspond to black holes of less than 10 to the 16 solar masses, which of course cannot be very abundant in the universe. Okay, but if you want to have 1 solar mass or 30 solar mass black holes, here you have no constraints. So this looks like you do have constraints, but these are projected constraints that you might have if you measure with SKA or the PTA, the effect that you would get from a lot of gravitational waves from primordial black holes merging on pulsar timing arrays, measurements of pulsars. But let's ignore these constraints. These are not constraints that exist. There are no constraints here, so you can actually form them. Okay? What you would have to do is you would have to take the primordial power spectrum of fluctuations, which behaves like this on these scales, and somehow you would have to boost it 9 orders of magnitude so that it's of order 1 here, because this is the range where you need to be in order to actually form PBHs. So you need to boost it somehow here, and then and then it has to drop again so that you would only form black holes in a particular mass scale. So that's kind of fine-tuned. This is the amount of fine-tuning needed, but it's allowed because there's no constraint. Okay. So why even consider this? So I like to show this comparison with the LHC. It took 2 runs of the LHC to be able to see this excess at around 125 GeV in the Higgs to gamma channel. We can try to do the same thing. I only talked about the first measurement of the black hole merger, which only had 2 black holes merging. So you can try to construct a mass function or a PDF for the mass of the emerging black holes using the measurements of these masses. Okay, so this is sort of the PDF of the two black holes that merged in the first event. And now I can play the same movie, and I can take the first two runs of LIGO, O1 and O2, and I can sort of try to accumulate the PDF of the masses from the black holes. And what you can see is that you get a rise towards 7 solar masses or so, and then you start dropping. But then there's another peak here, which you don't expect to get. You do expect things to rise and then fall, because if you think of the what's called the initial mass function, the PDF of stars in the universe, that's something that looks like this. It falls as a power law in mass. Okay, a negative power law of something like 2.35. This is a well-known result. So if you assume that the same thing that holds for stars also holds for the black holes that form from these stars, you would expect to get something that peaks here for small black holes and then falls and then falls. But you get this indication for a peak, and this is with just 6 events from the first 2 runs. These were the events that were first published. Then LIGO went into the data and extracted 4 more events from the data. And using 10 events, this is what the mass function then looked like. Okay, so it kind of seems like something is blowing up here on the 30 solar mass scale, so maybe we're seeing something. Of course, this is just 10 events, and it's nothing. And you don't want to make too much of 10 events. You know, talking about the 750 GeV excess yesterday, I would not necessarily devote my career to something that is based on 10 events, but still something is it looks like there's something interesting here. Maybe the explanation for why there's a bump in the mass function from merging black holes at 30 solar masses, maybe the explanation comes from something in astrophysics and not from primordial black holes as dark matter, but it's worthwhile thinking about it. Yeah.
Wouldn't this also be biased by sort of black holes that could form binary systems, for instance? I mean, that we would actually be able to, because if you just have a single black hole, you wouldn't be able to see it.
That's right. That's right. So if you actually want to predict what the observed mass distribution of black holes would be, you have to take into account not just the formation, you have to take into account the binary formation mechanism, and you also have to take into account the experimental sensitivity, or the experimental bias, because larger black holes emit stronger gravitational waves, and so they're easier to detect. So you do expect, you don't necessarily expect to detect, even if the IMF, the mass function of black holes looks like something like this, you don't necessarily expect the observed mass distribution to look something like this. And you have to fold in the binary formation mechanism, which is, it's a good question, but that's in the details. But again, if after 100 events we still have a peak like this, then there's something to explain, because it should not look like this. It might just go away.
Omega matter would change over time. Like all we expect black hole mergers to start at some metrics and then stop.
Well, most of the mass is retained. It just goes into black holes that have higher mass. Some of it is radiated. You're talking about the loss to gravitational waves, which is something on the order of 5% of the total energy. So no, it's something like 5%. There are papers that try to probe exactly this. So there would be a change. You're right. You're exactly right. The energy density in dark matter would change over time because of these mergers emitting. Some of the energy is emitted. Some of the mass is emitted into energy, into gravitational waves. So that's true. And there are papers that have tried to use this as a constraint, but the loss is too small to be detectable. It's about what? Sorry.
Can you get 7%?
That's interesting. I think there was a paper actually trying to tie it into the whole picture. I don't remember the details though.
So even this is relatively old at this point, right? We do have many more events now that
Yeah, but they haven't published the masses, so we don't know what the masses are.
So
We'll have to wait 3 more months or so. In April, they're about to. They're expected, or at least after April, once they shut down this run. We're now in 03, the 3rd observing run. When they publish the next results, then we'll have, well, right now they have like 35 or 40 events detected. So by April, they'll have maybe 60, 70 events. Then this will have much more statistics, and we'll see if the peak goes away or not. So now, how do you search for primordial black hole dark matter? You can think of an analog, which is how you search for dark matter particles, So you usually plot this diagram, and you can go about this diagram in different ways, right? Collider physics, indirect detection, and direct detection. And you can do the same for, my argument is that you can do the same for primordial black hole dark matter. So you can try to look for indirect detection of primordial black hole dark matter, which is when two primordial black holes collide or annihilate. What happens is they emit gravitational waves, and this is, so you can actually look at the gravitational wave signatures and see if you can use them to constrain the dark matter. Or you can look for direct detection, which, similar to here, where direct detection is looking at some standard model particle and the effect that an interaction with a dark matter particle would have on it. Here you would look at a standard model astrophysical object and think of the effect that some interaction with a primordial black hole would have on it. Okay? So in direct detection, you can think of the CMB. You can think of a lot of different things, and I want to just show you the fast radio burst before I finish. So to try to put constraints on primordial black hole dark matter, you have to consider what masses are possible to begin with. So this is sort of the range of masses that is potentially allowed for primordial black hole dark matter. This is where 30 solar masses is. You can't have them too small. If the primordial black holes are very small, smaller than 10 to the 16 grams, they would evaporate due to emission of Hawking radiation in less than a Hubble time, so they wouldn't survive till now. On the left-hand side of this interesting region of 30 solar masses, most constraints come from lensing. On the right-hand side, they come from dynamical effects and accretion onto the CMB. How much time do I have? 5 minutes? Okay, I think that's enough. So let me just describe how fast radio bursts could come into play. So for that, let me explain what microlensing is. So microlensing is the effect when we look at stars. We are on Earth, we look at the light from a star, and say that some mass, some primordial black hole, for example, or some other macho, this is relevant for any macho model, say that a macho or primordial black hole crosses our line of sight, or close to our line of sight to the star. If it does, and it's moving, normally objects move in dark matter halos with velocities of hundreds of kilometers per second. And the Einstein radius is given by, is related to the mass as the square root of the mass of the lens. If this happens, the light will be deflected from the star, and we will get a magnification signal, a lensing magnification signal, and you can calculate what that signal would be. So the light from the star that normally looks like this would be magnified over some amount of time, and then the magnification would stop once this lens goes away from our line of sight. Now you can use the dimensions, the only scales in the problem here, to estimate how long this effect would last. So this magnification effect would last, it turns out that it lasts of order years for lenses that are 10 solar masses or so. So that means that if you want to actually infer that you have seen a magnification of a star, if the lens is of order 30 solar masses, you need to observe the same star for years and years and years to be able to say that you had some flux, then it was magnified, and then it went back to the original. Okay, and we just haven't done that yet. We haven't taken measurements, continuous measurements of light from stars for long enough so that we can actually constrain using this simple method. This is called microlensing. Simple method constrain 30 solar masses. So maybe we can think of a different type of lensing effect to try to probe these mass ranges. And what you can do is you can look at fast radio bursts. So fast radio bursts they look something like this. What are they? They're literally fast. The width of the intrinsic width of the flux that you're seeing, the burst that you're measuring in radio frequencies is about 1 millisecond. So that's how long they last. They're in radio frequencies. That's why they're called fast radio bursts. And they're bursts of about 1 Jansky or so. That's the amplitude. We know now that they're extragalactic. So if we put some burst like this at the cosmological distance from us, something like on order of a gigaparsec or so, the inferred radiation emitted, if it's emitted isotropically in all directions, if it's not a jet, it's something like 10 to the 39 ergs. Okay? So that's kind of a lot. It's enough for them to actually be detected. It's not close to gamma ray bursts or things like that, but it's pretty powerful. But the important thing is not this. The important thing is that the rate of these things is huge. Okay? The estimated rate for these things is 10 to the 4 per sky per day. That means that 10 to the 4 fast radio bursts go through us every day.
What's the mean to this first?
We don't know. It's a very good question. We think it has to do, because of the short duration, we think it has to do with neutron stars, which are small objects that still can have some emission out of them by some mechanism, but we don't know.
If we don't know the origin, how do we know the energy they release?
Because we know the distance to them and we know the flux that we measure.
So this is like based on the luminosity rate.
Yeah. Okay. So another interesting thing about
Sky is 4.5, right?
Yeah.
So sky is 4.5?
Okay, another interesting thing about these fast radio bursts is that I was showing you the burst in one frequency. What actually happens is you measure something like this. So as a function of frequency, you measure the high frequencies coming in first, and then the low frequencies come in later. And this is because of dispersion. So the light is dispersed. This burst is dispersed. It's dispersed due to interactions with free electrons along the line of sight between us and the source. Okay, and the time delay, or the relative time between when the high frequencies arrive and when the low frequencies arrive is a function of this dispersion measure. It's a function of how many free electrons there were between us and the fast radio burst. This is also indicating immediately, forget dark matter now, what is this hinting at? What can you possibly maybe do with fast radio bursts? Use them as standard candles. That's right. Because if you can actually measure, if you can use this to estimate the distance, okay, if you think you know what the free electron distribution is across time, you can actually, this dispersion measure is a measure of distance, okay? And if it's a measure of distance, then you have a new type of standard candle. And people are thinking of using fast radio bursts as a way to measure H0. The only problem is that it's hard to separate, or the main problem is that it's hard to separate between what's coming, the dispersion that is coming from the intergalactic medium, and what's coming from the galaxy where the fast radio burst occurred. Okay, you can take out the effect in our galaxy because you know where the fast radio burst is coming from, so you know if it's coming through the disk or away from the disk. Just to show you the way that we inferred that these fast radio bursts are indeed cosmological, by now we know the origin of, we've detected the galaxies where some of these originate. So we know that we for sure know that they're extragalactic. But there was a huge debate over these bursts, whether they are extragalactic and cosmological really or not, that lasted several years. What was convincing is that if you look at the same dispersion happens for light from pulsars as well. But if you look at pulsars, if you look at the galactic latitude as a function of the galactic latitude, what the dispersion measure is like, you can see that if they're coming along the disk of the galaxy, then their dispersion measure is much higher. But if you're detecting them away from the galaxy disk, the galactic disk, then they don't have a large dispersion measure, so it's all coming from the galaxy. And these are nearby pulsars. These are galactic pulsars, or local group pulsars. But the fast radio bursts, their dispersion measure, it looks like this. So even if you look away from the galactic disk, you still see huge dispersion measures. Okay, so from this you can really infer that they are cosmological. By now it's something that we know. Okay, so how would you constrain machos or primordial black holes? The last slide. How would you constrain machos with fast radio bursts? They would also lens. Similarly to what would happen to microlensing of light from stars, if you have a source FRB and you have a black hole along the line of sight from us to the FRB, the light will be deflected. Instead of detecting one burst, you would detect two bursts, and what you would observe is some peak and then some smaller peak after some time delay. And it turns out that the time delay that corresponds, if you can calculate this, the time delay that corresponds to lensing by black holes of 30 solar masses is of order 1 millisecond or so. This is just a nice coincidence. So you would actually measure a burst and then another clean burst very close to it.
Didn't you just say 1 millisecond is the size of the burst itself?
That's right. So that's the nice thing. So
The one that you
okay,
calculate.
perfect. So if the black hole masses are if the primordial black hole mass is too small, then the time delay will be too small and the two peaks will be overlaid. So this is why you cannot use this to measure primordial black holes that are smaller in mass than about 30 solar masses or so. So below 10 solar masses, this becomes ineffective. But as long as the mass is larger, the time delay will be larger than the size of the duration of the burst, and then you'll see two distinct images. Let me just skip I said this in words. And so these will be the constraints that you can place with fast radio bursts. So this is the fraction of dark matter in primordial black holes as a function of mass, and with fast radio bursts, with about 1,000 or 10,000 of them, you would be able to completely rule out that 30 solar masses, this green line, dark matter is composed out of these things. Okay, so this is a nice. So even fast radio bursts can be used for the H0 tension or measuring the expansion rate of the universe. They can be used for putting constraints on dark matter. And I think, yeah, there's a lot to explore, and I'll end here.